material that someone else makes, across food or General Mills for a product. So we've been using it, and then we ran out of it, and then I asked them boss, like, can we get more of that? She's like, yeah, I can get you two. And I wrote that. She's a senior scientist. Everyone, like, she's really good with the.
Okay.
She's like, yeah.
Let's get started.
Great.
Where's half of the class? Or not even half of the class, I don't know. Okay, let's get started anyway. So today we're gonna cover, is this always showing like that here?
Yeah, see it head away.
Ah, there we go. Okay. So today we'll continue with protein analysis, part of proximate analysis. That's what you will be doing next week in lab. To get us started, I have a few questions for you. Which of the following absorb UV light? Do you remember from your, do you want to say? You want to give it a go? I thought you were gonna. No?
No.
No? Okay. Anybody wants to give it a go? Come on, Kevin.
I think it's A and C for sure.
Yeah, absolutely. So a tryptophan is aromatic amino acid. It's just to confuse you. I separated them here. So your aromatic amino acids are tyrosine, tryptophan, phenylalanine. So tyrosine is the most absorbing of UV light, followed by tryptophan, followed by phenylalanine. So these are the amino acids in protein that absorb UV light. But every protein has certain amounts of these amino acids. So all proteins, intact proteins, absorb UV light at 280. So that's one characteristic we kind of lean on when we're doing protein analysis using analytical methods that require absorption or the protein is measured via absorption. We rely on the absorption ability of these three amino acids in proteins. Okay. Another absorbing unit in a protein is the peptide bond. And peptide bonds absorb IR radiation due to the, again, they can change in vibrational energy that is specific for peptide bonds. So we can use IR to determine protein content if it is calibrated. And also peptide bonds absorb light at 220 nanometers. So that would be in the UV spectrum. So what do you remember about the peptide bond? Oh, what? You don't remember what the peptide? Okay, and brave soul.
All of the above.
All of the above? Are you sure, Ian? There's
No,
one.
not one.
But thank you for answering. Any? Go for it.
Just A.
Okay, so A is definitely correct. Okay, it's a covalent bond. And B? And B? What? What? No. No. Peptide bond is the covalent linkage between the carboxyl group of one amino acid and the amine group of another amino acid. Thought you covered this in food chem, no? Was that long time ago?
Please.
Okay. So anyway, you're not responsible to learn this in this class, but I wanted to highlight the peptide bond because it's important in protein analysis in some methods. Okay, so why is it important to analyze protein? Why do we care for this component? Carol.
Nutrition labeling and government regulation.
There you go. Sum it up in two answers. Very good. Yes. So on the protein label, on your nutrition label, you have protein. So we need it for nutrition label. We need it for quality assurance. We need it sometimes if you're claiming a high protein on your label, you have to have a certain percentage of protein. So in order to claim a high protein on your nutrition label, you have to have at least 4.2% of available protein, not just total content. So sometimes you need to know how much of that protein is actually biologically available, because different proteins are different in essential amino acids content, they're different in digestibility. So not all the protein we consume are biologically available. So it's very important. What else?
Like shelf life stability.
Shelf life stability. Can you elaborate how
Like
protein
physical characteristics. I mean, protein denaturation, like.
So, okay, so protein denaturation, you're talking about more protein structure and impact on functionality. In our lab, for example, we always look at how the protein functions. Is it a good gelling agent? Is it a good emulsifying agent? And all of these methods depend on how much protein we have in the system. So we measure protein in order to determine the functionality of the protein. We also, if we look at physiological activities of the protein, if it's an enzyme or if it's a source of bioactive peptide, you want to determine if it's an enzyme, you usually determine the activity of the enzyme per gram of protein, because enzymes are protein. So the unit of activity is per amount of protein. One other thing that we didn't mention is when we produce protein ingredients. So sometimes you label proteins as concentrates, you label them as isolates. What determines that label is the protein content. So concentrates, for example, whey protein concentrate, you have WPC for whey protein concentrate, you have WPC 30, you have WPC 50, you have WPC 80. So that number is 30% protein, 50% protein, 80% protein. And the cost of that ingredient increases with the amount of protein that is in it. Whey protein isolate has a minimum of 90% protein. So depending on the ingredient we produce and how we label it, we have to find out its protein content. Yeah, so there are different methods for analyzing proteins. We have the official methods of analysis, the Keldal and the DUMAS. Both are based on nitrogen quantification. These are the official methods that are either or used for nutrition labeling. So, and these are the methods we use to calibrate, for example, IR instrumentation, whether mid-IR, which is basically used mostly for dairy, and determination of protein using mid-IR for dairy, or determination of protein using near-IR, NIR, mostly for powder, high carbohydrate sample, you use calibrated near IR. Okay, there are other methods. The list is very, very long, and these methods, we call them research methods because you require the sample to be really pure, does not have interferences. So normally a complex food sample to determine protein content, we do not use methods that rely on a chemical reaction that potentially result in a compound that absorb light. So there will be other interfering substances in your sample that might absorb light at the same time. And all of these methods really are based on measuring absorption. And therefore your solution needs to be clear. So oftentimes it's not possible to get a food sample and to prepare an extract and all of your proteins is in this clear solution. That is kind of next to impossible. So therefore we do not use any of these methods to determine protein content in complex food systems. In the lab, you're going to do Bradford assay, but you're going to do it on a protein isolate powder. So although it has other potentially interfering substances, but it is a purified protein ingredient. So you're going to learn that assay in the lab, but you will be doing Caldal and DUMAS to determine your protein content in your different assigned food samples. So if we look at Caldal, Caldal is kind of the most ancient method for protein, one of my favorite methods of all time. Well, it's lengthy, but it has a lot of science in it, a lot of chemistry going on in it, and you're going to learn it with Coleman next week. Coleman in the back, he's one of my favorite students. And he's going to be me in lab. So usually I teach the Caldal section in the lab, but Coleman is taking over. And he is very experienced with it because he was tortured in doing that method for another assay. Okay, so it's based on determination of nitrogen content, and it has 3 major steps. You're going to learn this, and you're going to learn this by heart, because I'm going to ask this in the final. I'm going to guarantee you're going to get that question. What are the 3 major chemical reactions in Caldal? Digestion, neutralization, which is during distillation, you have a neutralization step, and then titration. So when I say what are the 3 major chemical reactions in Caldal, digestion of the sample, neutralization, followed by titration. The distillation is basically part of the neutralization step. Okay, so we're going to learn about this in class, and you're going to learn about this in lab. So by the time the final is here, you're experts in Caldal. Okay, so it's based on following the nitrogen. So all the chemical reactions that I'll show you, it's basically following the nitrogen and calculating the nitrogen content. Then we convert that to protein. How? Every protein, of course, has amino acids, and the different composition of amino acids leads to different nitrogen content. Why is that? Which amino acids potentially might cause differences in nitrogen content among all the amino acids? Because amino acids, all of them have an amino group and a carboxyl groups, but some amino acids have more amine groups. What are they? Do you remember? Chemistry, food chemistry. Carol.
Sarah?
Sarah. Sarah. Carol. Sorry.
I think lysine.
Yes, you think right. Lysine is a basic amino acid. There's 2 more. Carol. Huh?
I can tell you.
You cannot tell me? What? It's okay. Go ahead, Stella. Tryptophan. No, I like tryptophan, but
So would that not matter?
what's that?
Doesn't it have an extra nitrogen in it?
Oh. Ah, she got me there. But what I was talking about is 3 basic amino acids. These are lysine, arginine, and histidine. And those 3 amino acids vary a lot in different proteins. So the average nitrogen percent in any given protein is 16%. But sometimes we have higher the basic amino acids, and that would bring the nitrogen content to be over 16%. Sometimes it's 17, 18, 19%. So the higher the nitrogen content percentage in your given protein, the lower is your conversion factor. So, for example, wheat protein has really high amount of basic amino acids, whereas dairy protein doesn't have high amino acid, percentage of nitrogen. So the conversion factor for dairy, so those of you that will be doing cheese, your conversion factor is 6.38. So it's bigger than 6.25. So the nitrogen content is lower than 16%. Whereas wheat, you have more nitrogen due to higher basic amino acid content. So you have about 5.6 conversion factor. So this number here is higher, you get a lower conversion factor. So those of you doing Cheerios or baby cereal, you will have a different nitrogen conversion factor compared to the cheeses. So this is important to know. I'm not going to have you memorize nitrogen conversion factors, obviously, but I just want you to understand that that's one of the questions in your lab report is why different proteins have different conversion factors. And that's because we have different percent nitrogen in different protein, mainly due to the basic amino acids that differ among the proteins. Okay, so that's one thing I want you to know and remember is that utilizing the nitrogen content, we need a conversion factor to get us to the percent protein. Okay, and it's a crude method of detection. I'm thinking that Gary talked to you about what crude means. Do you remember when he introduced proximate analysis? So crude, rough, not accurate, because crude, this method is based on crude determination of total nitrogen, assuming that all the nitrogen is coming from the protein. All the amine groups is coming from protein, but there are other components that have amine groups. Vitamins, some vitamins have amine groups, some like urea, residual. So you might have nucleic acids. So you might have other sources of nitrogen, but we're assuming that all of them are coming from the protein. That's why it's not an exact measure of protein content. It's the crude protein content. However, it's official. I think somebody asked me what makes a protein, not just protein, a method, an official method of analysis. Does anybody know what give it the official designation?
I don't know if this is right, but isn't it that it complies with the AOAC method?
Yeah, what makes the AOAC method body approve this method? Stella?
Just like the amount of expensive research that
Yeah.
has been done.
Absolutely. In order for a method to become an official and adopted by AOAC or adopted by AACCI or adopted by AOCS, so whatever it is, it has to be done across different labs, has to be validated, and with a lot of data that proves that it is reproducible, it is precise, as accurate as can be, and therefore then it becomes an official method of analysis. So CalDAR has high precision, is very reproducible, and a reliable method of analysis. If you prepare the reagents correctly and you follow the steps, you can't go wrong, basically, with CalDAR. All right, so the first step is distillation. Okay, digestion. So during the digestion step, you have your food that gets digested with a very concentrated sulfuric acid with heat. So this high acid and high heat, what happens is you basically break down the components of food into gases. So you're going to see a lot of fuel generated. You won't see it, but Coleman's going to talk about the generation of fuel. So you will have a lot of fuel. This is basically you're combusting your food into CO2, H2O, and SO2. However, your nitrogen is going to be fixed as ammonium sulfate. So that's the term you want to remember. We're following the nitrogen, we're following the amine group. Okay, so basically, acid, heat, breaks down of the different constituents, you get a lot of fumes, and your amine groups are fixed in your solution. So they are fixed as ammonium sulfate. We use a catalyst, and the catalyst is made up of copper and potassium sulfate, sometimes copper selenide, and it's going to be blue because of that copper in there. So the catalyst, what it does, it increases the boiling point of your sulfuric acid. This is a very important thing to remember about the catalyst. It, of course, catalyst speeds up the reaction, we all know that, but in this case also it increases the boiling point of H2SO4, so that when you're heating, your H2SO4 does not evaporate too soon or too quickly and maintain its reaction with the food to digest. Okay, so the catalyst is very important to reduce the time and to increase the boiling point of your H2SO4. So that's the first step. Here we have neutralization happening along with distillation. So what happens here, we neutralize with NOH, and the NOH is going to react with ammonium sulfate, and it's going to give you ammonia in the form of gas. Okay, so the ammonia here in the form of gas is going to evaporate. So that's why we do a distillation where we make it a closed system, where the ammonia and water, because there's going to be heat during this reaction, the ammonia and water are going to evaporate, and then they're going to be distilled and collected. Because it's an ammonia gas, you don't want to lose it, and that's where your nitrogen is. Then you want to capture the ammonia. We'll see that later in an image, that the ammonia is going to go up in your distillation unit, gets distilled into a flask containing boric acid and a methyl red indicator. So methyl red and boric acid will give you a dark pink color. And then ammonia is going to react with boric acid to give you ammonium borate. This is going to change the methyl red color into yellow. So you're going to see nice color changes next week in lab. You're going to see a change from pink to yellow with boric acid and having ammonium borate. And then in order to determine the amount of nitrogen, the ammonium borate is going to be titrated with HCl, so acid. So you're going to titrate your yellow solution with acid to reach an end point. The minute you turn the page, you stop the titration, and that would be the equilibrium of the reaction. So at equilibrium, number of moles used for the acid equals the number of moles of your borate equals number of moles of your ammonium, and you have one nitrogen equals the number of moles of nitrogen. So basically at equilibrium, number of moles of acid equals number of moles of nitrogen, and that's how you can get the nitrogen content, because you have the volume of titration, you corrected with a blend, you have the normality of the HCl, you have the molecular weight of nitrogen, and then you have the weight of the sample. You correct milliliter to a liter by dividing by 1,000 milliliter, and then you get the percent of nitrogen. And from there, percent of nitrogen times the conversion factor gives you the percent protein. Okay, so I want to spend some time. Oh, before that, okay, this is the apparatus for digestion. You're going to see this in the lab where your samples will be already digested because it takes a lot of hours to digest and cool the sample before you can do the neutralization distillation step. So Coleman will be doing that part for you, where your samples are in individual tubes, digested with assay in a hot block to heat it up. And then the distillation unit that you'll be using is this unit, picture of it. I don't know why the pictures are not very clear, probably I should take better pictures. But what happens here is after digestion, you have a clear solution. It's blue because of the copper in your catalyst, but your nitrogen is fixed as ammonium sulfate. Then, and then there is water as medium. You put in there NaOH. The NaOH is going to neutralize excess acid and going to react with the ammonium sulfate. There's going to be heat generated due to steam. And then what you're going to happen here is your ammonium sulfate reacting with sodium hydroxide, then you will have ammonia and water. So water is the carrier, basically vapor going through the distillation unit, gets distilled into your beaker containing your boric acid with methyl red indicator. And then once you have ammonia, the color starts changing to yellow. That's basically what's happening. This is an old unit actually that I used when I was a graduate student. Really old digestion block unit, and then you have the distillation on top. It's very hazardous. So glad that's no longer used. Anyway, this is the equation, the calculation. I'm going to derive it for you a little bit. What we said, I'll walk you through this, because if you know the derivation of the equation, you will remember it, and you need to remember the equation for calculations. So we said at equilibrium, so you have, what? Doesn't work. So you have the ammonium chlorate reacting with your HCl. At equilibrium, you have here one nitrogen. So number of moles, let me write it out. Number of moles equal of this equal number of moles of HCl. Okay, so that's equilibrium. That's what you, number of moles of nitrogen, just to be clear. So that's it. At equilibrium, number of moles of nitrogen equal number of moles of HCl. So you need to remember number of moles equals mass over molecular weight. I'm looking for this. I want to know how much nitrogen I have to calculate the percentage. I have the weight of the sample. I need to know the weight of nitrogen. Okay, so I'm after the math. Okay, so of nitrogen. If I'm looking for this, then I need to go N times molecular weight of nitrogen. Molecular weight of nitrogen is 14. So I'm looking for this. I need the number of moles, and then I have the molecular weight as given. All right, number of moles of nitrogen equal number of moles of HCl. So number of moles of HCl equal normality or molarity in this case are equal because we have one hydrogen times volume. Okay. This is in milliliter, but I want it in liter. Okay, I divide by 1,000 because number of moles is per 1 liter. So you have the molarity per 1 liter. Okay, molarity equals number of moles per 1 liter. So that's why I need to divide by 1,000 milliliter. That's why you have here 1,000. There should be a unit here, milliliter. Okay, so, and then that's number of moles. And then I have the molecular weight. Now I want to get the percentage. So therefore I have to divide by weight of sample. And multiply by 100 to get the percentage. So weight of sample you get in grams. Here it is moles per liter. Okay. And then here you get the molecular weight, which is grams per mole. So that's why it's important to know the units. Here, mole and mole will cancel. And then milliliter by milliliter will cancel. Then you will have gram per gram times 100 will give you the percentage of grams per 100 grams of sample. It says here corrected because you take the volume of HCl needed to titrate your sample and subtract the volume of HCl needed to titrate the blank. There will be a blank that you will be running next week because you want to correct for any nitrogen contamination in all the reagents that you use. Okay, so therefore we subtract the volume of the blank. That's why it's called corrected to get that. Any questions? No questions? That means you're good. I can repeat any step. Okay. Let's practice. Pull out a piece of paper, write your name, and at the end, give it to Brittany. Oh, yeah. So one thing I would tell you when you're doing samples in replication, you calculate each rep separately, then you take the average. All right, do that. And another thing in this question, please note that the sample has been dehydrated. That means it's been dried for you before you did the analysis. So your value will be on dry basis. You want to convert to wet basis using knowing that the moisture content is 8% of the original sample. So this is practice for you because you'll be doing a lot of calculation, dry to wet, wet to dry in the lab for your report. So that's practice. Anybody with an answer? No? Potentially? Yeah, yeah.
On average, I'm getting 21.6% for wet basis.
For what basis?
Yeah.
What was it before you made that calculation?
Before I make one calculation.
To what basis?
Oh, was that how it was originally calculated?
We are calculating on dry basis because it's dehydrated.
Oh, excuse me. That is dry basis. Yes.
There's something a little off with the number.
I got 19.6.
Yes, this is it. So basically you just apply the calculation here, you apply the numbers, you have all of the given. You have the molarity, which is moles per liter. And then you have the corrected. This is the blank, this is your sample for one of the rep. This is the weight. This should have a milliliter here, 1000 milliliter to convert to liter. And then 14 grams per mole. So mole will cancel with this mole. The milliliter and milliliter will cancel. And then you would have the grams per here. You get the first one. And in this case, you are multiplying by the conversion factor, which is 100 divided by percent nitrogen. So you get 19.62. And for rep 1 and rep 2, the same. You do the same, and then you take the average. Now the average is going to be 19.7. Potentially. And then, yes.
Where do you get 17.5 from?
Oh, it's in the question. The 17.5% nitrogen.
Oh, excuse me.
So you want to convert that conversion factor, you can do that by 100 divided by 17.5. Then you get the conversion factor, and then you have your reps. Now, this value that we've gotten, the 19.7, is on dry base. In 100 grams of dry matter. So 19.7 grams in 100 grams of dry matter. So when the sample is moist, we have 8% moisture, so we have 92 grams dry matter. Then your wet bases would be, so basically you're solving for X here. And you do cross multiplication. So that's what you're looking for. Times 92 grams divided by 100 grams. The 92 is 100 minus 8. Okay, then you get the value on wet basis. So you take the average of the reps. You have this on dry basis because we said dehydrated. And I gave you the 8% moisture. So 92 is the dry matter in 100 grams of wet sample. And if you have 19.7 grams and 100 grams of dry matter, so that is 19.7 grams in 100 grams dry matter. Then here you have 92 grams. That's the 100 minus 8. And then you get your wet basis. Your wet basis is always lower than dry basis percentage. If you remember that, you will know that you did the calculation correctly. Wet basis is always lower than dry basis because you always have some moisture. So your weight of dry matter in 100 grams of wet sample is less than 100, so the value is always less on wet basis than dry basis. Questions?
Could you go back one just for a little bit?
Back
Yeah,
one?
just-
Okay. Make sure, put where I missed the units, put your units, so there's really here. You have a question?
So you're taking, so then on the next slide, we're going to take the average of those two 19%, right?
Yeah, you always calculate each rep individually, then you take the average, and then you would convert that average to wet basis. We good? Okay. The other method that you will be doing in the lab is measuring nitrogen content. We're using a nitrogen combustion method. And it's called DUMAS, and we use a nitrogen analyzer to determine the total nitrogen content. And basically, it's a nitrogen combustion, so your sample is combusted at really high temperature. So you will use small capsules, you'll weigh your samples in these small capsules, and you will put them in this sample wheel. Well, this is an old nitrogen analyzer that we had. We have a fancier one now that we're working with in the lab with a fancy screen and everything. But anyway, the same principle. You have your sample, it gets dropped, each sample at a time, it gets dropped and gets combusted at really high temperature, over 900 degrees Celsius. And then it gets combusted into gases, NO2, NOx, and CO2 and H2O. So all of your sample is being combusted into gases and then cooled down, but the gases are transferred and cooled down, and then they go into a ballast where your gases are mixed and homogenized. You do have a carrier gas, helium in this case. And then what happens after they're homogenized and mixed, they go into reduction tube with copper to reduce NOx into nitrogen gas, N2. So then you will have nitrogen gas, you have the CO2 and H2O, they go into scrubbers, one for CO2 and one for H2O or vapor. And then your nitrogen gets detected using a thermal conductivity detector. So it's kind of like the GC detector that you've learned about, where it measured changes in conductivity. So you have your helium as a carrier gas, and then when nitrogen passes, then the change in conductivity happens, and that gets converted to the content of nitrogen in your carrier gas. Sometimes you don't have scrubbers, you actually have a GC column, but we don't have that. We have scrubbers that will basically scrub off all of the other gases, and only nitrogen gas makes it to the thermal conductivity detector, and you get results in a very short period of time, basically. You will learn about this nitrogen combustion method with Brittany next week in lab. So you will have your samples, you will run them in duplicate, and you will get results really fast. Calgal takes a long time in comparison to DUMAS method, but in terms of accuracy, precision, reproducibility, they're both very good. That's you will have comparable results, more or less. using the two official methods of analysis. This is kind of just another diagram that shows that you need air and CO2, and then you basically get that combustion happening, and then you need a carrier gas, which is helium, and it's just a demonstration what happens if everything gets scrubbed off, and you don't have a column, you just have scrubbers, and then you would have detection by thermal conductivity detector. So oftentimes you might be asked if you want to compare Keldal to DUMAS. You want to think about the principle. They're both based on nitrogen determination. However, one is nitrogen combustion and the other one is chemical reaction. You need an expensive instrument that is very temperamental, so requires high maintenance, very expensive. So that's why LICO, or not, LICO is the company. The DUMAS method to get that instrument, it's really high in cost. To maintaining, it's also high in cost, but it has really high throughput. So oftentimes you have hundreds of samples to run, can't afford the time to use Keldal to run. So nitrogen combustion does not require chemicals, whereas Keldal do, and very concentrated acid and base reagents. So we need to follow safety protocols. And in terms of application, you can alternate. You can use one or the other in terms of again, accuracy, precision, reproducibility. So both are good in that respect. So you want to think about knowing the principle of these two methods to be able to compare them. Know that DUMAS requires very expensive instrumentation and maintenance. However, high throughput, no chemicals, similar application. So you want to remember that. I'm going to stop here for now, and we can continue on Monday. All right, have a great weekend. We have a question, Sarah.
Clarify, you said both of those are pushing, right?
Yes.
Okay.
Yep.
So that.